Hello, calculus fans. Okay, so we're able to solve quadratic equations very easily. There's even a lot of different ways we have of solving them. We can factor, we can also complete the square, and when all else fails, we can always use the quadratic formula. And then there's lots of other equations that can be solved in other ways. However, there's all kinds of equations that are just impossible to solve, at least to come up with an exact solution. For instance, there's no way of finding exact solutions to this equation. It's a fifth-degree polynomial. There's no fifth-degree formula like there is for solving a quadratic formula. So what we're going to do is say that instead of finding exact solutions to equations like this, we're going to try to find approximate solutions. What we'll do now is describe one of the more famous solution methods, and this is called Newton's method. All right, the idea behind Newton's method is that we're trying to find a root of the equation f of x equals 0. So we'll start with a guess for what the root is. We're going to call this guess x1. We'll use that guess to create a better guess, which we'll call x2. And then as we'll see, we're going to use this better guess x2 to create an even better guess x3, and then this process can continue on indefinitely. The farther along we go, usually the better the guesses will be, the closer they'll get to the actual roots. So let's show using a picture how this works. Okay, so in this picture, we have a graph of a function y equals f of x, and you can see that down here there is a root. That's the place where the curve hits the x-axis. We're going to try to approximate where that root is. So we'll start with a guess. This is x1. It's a guess of where the root is. Now in this picture you can tell that this is not a very good guess, and we're going to see how we can improve on this guess. Essentially what we're going to do is find this tangent line to the curve at x1, and we'll see where that tangent line hits the horizontal axis. And wherever that tangent line hits, that's going to be our new guess. And you can see in this picture that the new guess, x2, is an improvement on the original guess, x1. All right, so starting with our initial guess, x1 for the root, we find the tangent line L to the curve at the point x1, f of x1. Wherever that line L hits the x-axis is going to be our new guess, x2. Usually, x2 is going to be a better guess than x1. And again, usually, if we keep doing this, we're going to get closer and closer to the value of r. Now let's keep going. Let's find a new tangent line at the point x2, f of x2, and let's just see where that tangent line hits the x-axis. We'll get our better guess, x3. So here's the revised picture. So you can see that we've computed the tangent line at x1, f of x1, and that has hit the horizontal axis down here at x2. And now we go up to the point x2, f of x2, and create a new tangent line. This new tangent line, which is the one in blue, now hits the horizontal axis down here at x3, and that's our new guess for the root. And you can see in the picture that this time we've gotten really close to the root. It's actually a little bit difficult to see where the actual root is and where the guess is. They're very close together. And as we keep doing this, we get ever better guesses for the root. So what you should see in the picture is that x2 is a better guess than x1, x3 is an even better guess than x2. All right, let's now derive a formula for how we're going to get from x1 to x2. What we'll do is we'll write down an equation of the tangent line, L. That's the tangent line to the curve y equals f of x at x1, f of x1. Okay, so we're writing down an equation of the tangent line, the first one that we talked about. Well, we know the slope of the tangent line is f prime of x1. The line passes through the point x1, f of x1. Remember, we only need two pieces of information to be able to write down an equation of the tangent line. Okay, so we get the equation y minus f of x1 equals f prime of x1 times x minus x1. Now remember what we're trying to do. We're trying to find the x-intercept of this line. So we just plug in y equals 0 and solve for x. Now you should work through the algebra. Put a 0 in here and solve for x. We'll end up with this equation here. X is equal to x1 minus f of x1 over f prime of x1. You should take the time to work out that algebra. Now this new value of x is going to be our new guess for the root. And our new guess, we've called it x2. So that tells us that x2 is equal to x1 minus f of x1 over f prime of x1. Now notice this only works as long as f prime of x1 is not equal to 0. Now we could do this again, just as we had in the picture, and we get a similar formula for x3. So now we have that x3 is equal to x2 minus f of x2 over f prime of x2. So we're going to say that in general, if we have the nth approximation, and it's x sub n, and as long as f prime of xn is not equal to 0, then we can say that the next approximate value is going to be x sub n plus 1 equals xn minus f of xn all over f prime of xn. If the numbers x sub n get closer and closer to r as n gets large, then we're going to say that the sequence of numbers that we generate converges to r, and we'll write the limit as n goes to infinity of x sub n is equal to r. Now I would point out that Newton's method is not foolproof. There are ways that it can go wrong. The most obvious way it can go wrong is that one of these derivatives ends up being 0. And the book shows a few other possibilities for what can go wrong. But in general, it's actually pretty robust, and it will work on a large class of equations that you're trying to find roots of. That's all for now.